Good morning, students. I am back with another session on chemical bonding. Last class we discussed about formation of chemical bonds by sharing of electron pairs, covalent bond formation. Now, the two types of bonds we discussed do not completely explain why the valence electrons are involving themselves in the bond formation. To explain this concept further, two theories were put forward and were refined 2 or 3 times to give a more comprehensive view to predict the shape of molecules. Though this theory theoretically cannot explain how the bond is being formed, but it makes an attempt to explain shapes of molecules by showing you bond pair electrons and lone pair electrons. The theory called as the valence shell electron pair repulsion theory, commonly called as whisper theory, was put forward by Sidwig and Powell and further refined and improved by Nome and Gillespie. The theory was put forward by Sidwig and Powell and refined by Nome and Gillespie. This whisper theory talks about the concept of electron pairs present in the valence shell involving themselves in bonding or not involving themselves in bonding. Those electron pairs which are present in the valence shell which involve themselves in bonding are called as bond pair electrons, and those which are present in the valence shell but do not take part in bonding are called as lone pair of electrons. Now the valence electrons are present as pairs around a circular pathway called as the shell. They reach a position where the repulsions are minimum. If more than a bond is to be formed, then multiple pairs of electrons are said to be a super pair. These are the postulates of the whisper theory. Based on this, the molecules were classified into 2 types. A set of molecules where the central atom involved in bonding does not have any lone pair of electrons. They have only bond pair electrons. And second, the molecules which have at least one lone pair of electrons on the central atom. Now, what do we mean by a central atom? Central atom is that atom which involves itself in bonding by sharing electrons with other atoms. It is a central metal atom or a non-metal atom depending on the type of molecule which is being formed. Now, let us see some examples of molecules which were given appropriate shapes based on whisper theory. These are molecules where the central atom does not have any lone pair on it. Example of a linear molecule. This is beryllium chloride. Look at this molecule. The central atom here is a beryllium atom. It is bonded to 2 chlorine atoms by sharing a single pair of electrons. This molecule is a linear molecule and the central atom beryllium has 2 electrons in valence shell which it shares mutually with 2 chlorine atoms, leading to beryllium chloride molecule which is a linear molecule. The second molecule which we will discuss is boron trifluoride or aluminium trichloride. The central atom, aluminium or boron, has 3 electrons in the valence shell. It is sharing the 3 electrons with 3 chlorine atoms. So, boron trichloride, boron trifluoride if the atoms are fluorine atoms, or aluminium trichloride if the central atom is aluminium. So we have a molecule of trigonal planar shape, where the central boron atom is bonded to 3 fluorine atoms by sharing single pair of electrons. Then we have our old friend methane molecule. The central carbon atom is bonded to 4 hydrogens by 4 single bonds. The molecule shows a tetrahedral geometry. Then we have phosphorus pentachloride, PCl5. The central phosphorus atom has 5 electrons in the valence shell. These 5 electrons are shared with 5 chlorine atoms to complete the octets. Now 3 chlorine atoms are on the plane, and 2 atoms which I have shown with a slightly larger bond are perpendicular to the plane. So the molecule looks like trigonal bipyramidal. It's a trigonal bipyramidal molecule. The bonds here are longer than these bonds. The bonds on the plane are called as equatorial bonds, and the bonds perpendicular are called as axial bonds. Axial bonds are always longer than the equatorial bonds. This is because of the repulsions between the chlorine atoms. To avoid that, the bonds become slightly longer. Next comes the molecule of sulfur hexafluoride. Its octahedral geometry. The central sulfur atom has bonded by sharing its 6 valence electrons with 6 fluorine atoms. So SF6 is an octahedral geometry with 4 on the plane and 2 perpendicular to the plane. So when you join this, it becomes an octahedral geometry. These are molecules where the central atom does not have any lone pair on it. Whatever the electrons are present in the valence shell are completely involved in bonding, and those pairs of electrons we call them as bond pair electrons. Now students, coming to molecules where there is central atom having a lone pair of electrons. It can be 1, 2 or more than that. We will restrict ourselves to few examples which we are familiar with. Let us start with the example of sulfur dioxide molecule. If you look at the central atom sulfur, it has 6 electrons in the valence shell. It shares 2 pairs of electrons with 2 oxygen atoms each, so that the 4 electrons of sulfur are completely used up, forming double bonds with oxygen. But still, a pair of electron remains, and this is depicted as a lobe of electron cloud which is seen on the central atom. I am representing that in the form of a blue dumbbell-shaped structure which I am calling as the lone pair of electron. I have shown this dumbbell because the electron cloud is in the form of this. The lone pair of electrons have more region of repulsive area around them. Now if you take the central black atom as sulfur and these 2 white ones as oxygen, the sulfur dioxide molecule formed shows a bent structure. The expected angle of a bent structure is generally 120, but this molecule has 119 degrees angle, 119.5 to be precise. This is because of this lone pair of electrons on the central atom. This type of molecule is called as AB2, E representing the electron pair. In the CBSE book, there is a complete tabular column given with these molecules. Now this molecule is AB2E type of molecule, where A represents the central atom, B2 represents the two oxygen atoms involved with sulfur atom, and E represents the electron pair. The shape is bent shape. The next molecule I would like to discuss is our old friend ammonia. Nitrogen molecule has 3 electrons which it shares with 3 hydrogen atoms. After that, a lone pair remains, which is shown by this. So the expected geometry of the molecule is tetrahedral, but it becomes trigonal planar. This is because of the electron pair which is present on the central nitrogen atom. The bond angle is expected to be 109, but decreases to 107. Coming to the next molecule, water molecule. The central oxygen atom has shared 2 electrons with 2 hydrogens, but the 2 pairs of electrons, lone pair of electrons, remain on the oxygen atom. Now these 2 lone pairs try to be as far away from each other as possible to avoid repulsions. Now the repulsions here are not only between lone pairs but also between lone pair and bond pair. To minimize the repulsions, the bond angle expected is 109, but it reduces to 104. So the water molecule shows a slightly lower bond angle when compared to the expected 109. This is because of the lone pair repulsions. The next molecule is AB4E type. AB4E type. What do you mean by AB4? Now this is SF4 molecule. The central sulfur atom shares its 4 electrons with fluorine atoms, and a lone pair remains. Each sulfur has 6 electrons. Out of the 6 electrons, 4 electrons are used by bonding with fluorine atom, and a pair remains as a lone pair. To avoid the repulsions, the molecule changes its geometry and it looks like a seesaw. When we were small, we played on this, isn't it? This is the central handle. These two will be the 2 children sitting on it, and these are the legs of that. So this is called as a seesaw model. You go up, you go down. The molecules, the atoms of this also show such type of behavior. So this is a seesaw model. Now this same electron pair can be in the axial region, but it won't have that stability. The seesaw, where it is on the equatorial region, is more stable than the axial one. The next one is AB3E2, where 2 lone pairs of electrons are there. This is AlF5. Now the central chlorine atom has 2 electron pairs on it. The molecule shows the T-shaped geometry. See the T-shape. The 2 lone pairs are as far away from each other as possible. Then we have the molecule of IF5 or BRF5. There is 1 lone pair, and instead of the octahedral geometry, you are having a square planar with a 1 perpendicular to the axis and the other one is occupied by a lone pair. The geometry becomes square pyramidal. The last one is square planar, xenon fluoride. Xenon central atom added to 4 fluorine atoms with 2 lone pairs. Should be octahedral but becomes square planar. The 2 lone pairs occupy the perpendicular positions. I hope you have understood, children. With this, we come to an end of Vesper theory. Thank you.